Hello everyone, today I will try to explain the activation functions. What are the activation functions, way to use these functions, and how, and what's the benefit of these functions. Let's start. Oh, sorry. Yeah, activation function is decided whether this neuron has to be activated or not. So it means we will study this. If this input, for example, input, it's important to this to the next neuron or not. So this is the main function, the main functionality of activation functions. Sometimes you will find, for example, if you have a network and one neuron or many neurons will be non-activated, maybe zero. So it means it's not important for the prediction. So in a simple way, in a simple description, the activation function is that if you have input and for this input you have an output. For instance, let's assume this we have this small network and we have weight and height to predict gender, man or woman. And based on this equation here, we will try to firstly to start to find this neuron H1, and we have firstly we have to multiply weight multiply W1 and height multiply W2 to find E1. And now this H1 has to be activated. We use the activation functions to and make it the output of the. This is the input E1, which is this equation, and the H1 is the constant as an input to the next layer. I would think. Yeah, and what's the purpose of this activation function? The purpose of this is to add non-linearity. So if we assume that we don't need or we don't use activation function, it will be a similar applying this equation here, and all of these neurons and layers will behave the same, and we will not able to learn a complex model or complex scenarios. So it means activation function is needed. And here's what's the how we can choose and how we can see this is a good activation function. A good activation function must be continuous. So for example you have x, for example you have here x, and you have to have a value in y. It's impossible to have x but no let's say no output. And the second one, it's never changing direction. For instance, you can see here we have x and here's a y, x y x y. It's somehow increasing. If you have x, increase x means increasing y. But if you see here in this figure here, it's decreasing x, decreasing y, and increasing x, increasing y. This is not good. So it's confusing, I would say. So the good activation function has never changing direction, increasing like this, or might be decreasing like this. I mean, one of this. There it's decreasing or just only increasing. And non-linearity. What we mean by non-linearity? For instance, if we have here x, 2 multiply x plus 5, it's all you just only apply this formula here. You will have you have an x and you will have y, and this is non linear thing. It means we will remove the negative values here. The negative values here will be 0. Any output of x will be 0. X will be minus, the x will be y will be 0. Yeah, and let's start with nonlinear activation functions. For instance, the first one is sigmoid or logistic regression. It takes any real value and the output will be 0, between 0 and 1. So you can see here, this is for example any value of x has to be any value, but the output will be between 0 and 1. This is the formula here. of the sigmoid function. Uh, what is the pro of this of this activation function is that if you would like to predict the probability, you can use this sigmoid function in the output layer. And as you can see, the function is differentiable. So it means you have somehow, if you see this, the differentiable between 3 and minus 3 here. So it's not fixed as 1 or 6, or it's not a fixed value. So we have here the interval. And the disadvantage of this is that somehow the gradient, I mean, we'll learn how the gradient is working, for example, to updating the weights. But as you can see here in this figure here, the values, I mean, might be the values is close to 0. So it means that the network will not be able to train, and this problem is called vanishing gradient problem. So we have to find another let's see, activation function. And I'm assuming this is only for explanation how the activation function is working. So this is a normal equation. Just apply, for example, we'd like to find h1, this one here. This is the value 38.6 before the activation function. If we apply the activation function of the sigmoid, the value will be like this. So the probability, I will say the probability will be 2.69. I mean, only in this neuron here, and this 0.2 will be as an input to this. So 0.2 multiplied by W5, which is it's not clear, it's not defined here, plus B3 equals some values, any value. Then we will apply, let's say that, for example, sigmoid function, and this is the probability. If the probability is, for example, greater than 0.5, it's a male. This 0.5 will be somebody, for instance, woman. And the next activation function is tangent function. It's similar to sigmoid function, but the output of this function is between 1, you see here, 1 and minus 1. And the advantage of this, it's the data is centered, zero centered, so here is a 0. But if you see, for instance, the sigmoid is a 0, but it's not centered. So the data is centered in the sigmoid tangent, it's 0 centered. It means if the output, for example, positive, you can see, yeah, it's good. I mean, it's just as example. And if it's 0, it's natural, and if it's minus, it will be, or negative, it will be somehow negative feedback. Let's see. And usually this activation function used in hidden layers, not as in the output layers. Yeah, and the disadvantage of this, it's also the same as sigmoid, but somehow we see this interval is somehow larger than the sigmoid function. And the next one is ReLU function, rectified linear unit. And the main idea of this function is that if you have any negative value of x, it will be considered as 0, and we take only the positive only positive values. And means, if, for example, neuron has a negative value, it means it will not be activated, it will be disabled. So it means it's not important for the calculation, I will say. And the advantage of this, it's computational efficient. So it's just taking the maximum value. So there's no calculation, for example, for this. And it's try to converging to find the global minimum of the gradient, to find of the loss function. And the disadvantage of this one, any negative value will be zero. So most of the, not most, but some of the neurons, what might be needed for the calculation or for the prediction, it will be disabled. So the model will not be learning any further complex, let's say, scenarios. And this is leaky ReLU function. It's one of the, or let's see, is extended of the ReLU function in the previous slide, and you can see we need some negative values, slope values here. This is the formula here, and yeah. So the advantage of this, as you can see here, we need some negative values and some, or maybe the neuron will not be disabled. And the last one I will see, I mean, there's a lot of activation function, but I'm focusing on the most frequently used by any researchers on in production. So softmax function is calculate the probability. So if we remember from the previous slides, we had sigmoid function. Sigmoid function is to find the probability of h of x, for instance. And let's see here we have several classes: class 1, class 2, class 3. And if we see this value here, this is not between 0 and 1, and we need to find the probability of this, which class, let's see, 1 or 2 or 3. The idea is to use this softmax, and we find this, for example, the formula, it's the exponential of the value of this value here divided by sum of these values. You will have the probability. We'll do it for the next class and for the fourth class, for the third class. So for instance, we have three classes here, and the value, the sum of this value has to be 1. And for instance, now we will see, based on this calculation here, the high probability, it should be class 1. So we will assign this table or this an instance of data to the class 1. And we have here some activation functions. For example, this is identical. X it's equal to y, and here's the ReLU function, sigmoid function, and etc. And additional to that, so for instance, we have let's say we have some problems. Based on the problem, we can define which activation function we can use. So for instance, if we have a regression problem, so for instance, to predict I don't know, to predict the values, we can use linear regression in the output layer. And if we have a classification, for example, binary 0 or 1, male or woman, car or not car, normal or abnormal, so we use sigmoid function. But if we have many classes, multiple classes, we can use softmax. Yeah, that's it. So thanks for your watching, and see you in the next videos. It will be, I think, gradient descent or loss functions. Yeah, thanks, and see you later. Bye bye.